Hi there, welcome back to the formulaic approach. Now in this video we are going to be covering dynamics. So practically almost all you need to know on dynamics. You remember that we started our mechanics series recently, and under mechanics I did tell you that we're going to be seeing three aspects, which were the kinematics, the dynamics, and the statics, or statics rather. Now the statics is the aspect that studies equilibrium, bodies in equilibrium, and dynamics is the one that studies motion, forces that lead to motion, that cause motion. Is that okay? And that's what we want to do today. Then we have kinematics, which we just covered, the aspect of motion that doesn't without reference to the forces that cause the motion. Okay, so we have covered it where we did linear translational, horizontal translational, vertical translational, or vertical linear. Then we also saw two-dimensional, that is in projectile that we just saw. Then we also saw circular motion. Circular motion is both under dynamics and kinematics, because we saw the kinematics and saw the dynamics, the forces also. Then we also saw simple harmonic motion, which is under both as well. So now we want to see dynamics, which will study the forces. So dynamics is the one that studies the forces. It studies the forces that causes motion, or forces that influence motion. Is that okay? They influence motion. All right. Now, it should be noted that the three laws of Newton, the three Newton laws of motion, the three Newton's laws of motion will be of immense consequence here. Three Newton's laws of motion. So they will be of very good use here. We are going to refer to them a lot of times. So especially in this first category where we are going to be seeing, these are things we are going to be seeing. We'll see Newton's laws of motion, first Newton's law of motion, which has to do with inertia. We'll see second law of motion. Now in that second law of motion is where we deal with momentum, but we might not really deal with linear momentum well in this one, but we'll deal with motion on different surfaces, pulleys, inclined plane. And you see, I want you to stay till the end, because there is no way you watch this video and you will not be able to answer any question, I promise you, on pulleys, inclined planes, Atwood machine. There is no way you will not be able to answer any question on it. Just trust me. Then we'll also deal with motion in an elevator. So that's probably where we are going to stop. If there's still time, if it's not too long, I may still continue into linear momentum in full, where we deal with collisions. All right, so let's get into it. Now, let's state the first law of motion. Now, the way you state the first law of motion, the laws of motion will depend on what you want to, they basically mean the same thing, but I like to state it in a way that is easier, okay? So for example, the first law of motion simply says that all objects in the universe will remain in a state of rest or uniform motion unless acted upon by an external body. Maybe I should write that. All objects in the universe, all bodies in the universe will remain in a state or condition of rest or maintain constant motion or uniform motion or uniform speed unless acted upon by an external force. Okay? Now, others will state this law this way, that a body will keep doing what it's doing unless a force causes it to change. So it means that the summary of what the first law is saying is that it causes, it takes a force to cause a change. It takes a force to cause a change. So that is the summary of what this is saying. And this law is also called the law of inertia. It's also called the law of inertia. Now, why is it called the law of inertia? It is called the law of inertia because what does inertia actually mean? Inertia simply means rest, right? In fact, I think the origin, the word from which it is derived from, which is inert or inertia, is like saying that the body is lazy, not wanting to react, not wanting to change. Is that okay? Resistance to change. That's mean of inertia. Exactly. So the measure of inertia is the measure of inertia is a measure of the degree of resistance to change of a body. Okay, now practically we know that at the end of the day it is the mass of a body that constitutes in its inertia. So the greater the mass of a body, the greater the inertia. So mass constitutes mostly to the inertia of the body. So the greater the mass, the greater the inertia. The less the mass, the less the inertia. So of course, when we treat rotational inertia, we're going to know that inertia, moment of inertia is actually mr squared, given that the distance away from the axis of rotation is actually of immense consequence to the amount of inertia the body the body possesses. So, but we know that primarily one of the mass is innate to mass is innate I use now. Mass is a fundamental property of matter, right? Every matter has mass. Okay, so there are two things that are actually fundamental properties of matter. We have mass and charge, but actually not all a matter may not have charge, but will always have mass. Is that okay? Because mass is the quantity of matter in the substance. So it means that the measure of inertia is actually the quantity of matter, measure of the quantity of matter in that body. So the mass is the quantity of matter, and mass is the quantity of matter in a body. Is that okay? That the body has. Now I'm trying to go this way so that you will understand stage by stage. Exactly. So if a body is resistive to motion, it is because of the mass of the body. So meaning that if I exert a force on an object to move an object, and an object that is this small, okay, and I'll exert the same amount of force on an object consisting the same material of this size, then this one will be more resistant to the change that I'm trying to cause it than this other body. Do you understand now? So that is what inertia is. This one. So this body will be more this one here, body, if I call this body A and this body B. Now body B will be more resistant to change than this guy because one, they are made up of the same material according to my example, but look at the sizes. So this one will definitely contain more matter than this guy. So the more the quantity of matter in the substance, the more the mass of the object. So the more the mass, the higher the inertia. Is that clear now? Okay, so that is on Newton's first law of motion. Now you see, Newton's second law of motion is an extension of the first law. It's like, is in a way, it still relates to the second law, to the first law. So the second law will state that the first, there are different ways of stating it too. I can say that it takes unbalanced forces to cause acceleration. I can state it as simple as that, and it's still correct. So actually what it states is that the acceleration produced on the body is that the force acting on a body is directly proportional to the acceleration produced by the body. The force acting on the body is directly proportional to what? The acceleration produced. Okay? Now, one thing that you should know is that when we say the force, we're actually talking about the net force. We are practically talking about net force in this perspective, because in this context rather, because when force, there might be more than one force acting on a body, and this is where our work really starts. Now, the net force causes net acceleration. Is that okay? Net acceleration. Now, when there are many forces acting on the body and they are balanced, so when balanced forces act on the body, when balanced forces act on the body, when balanced forces act on the body is said to be in equilibrium. So when the body is in equilibrium, then the body remains at rest. The body remains at rest. And that's what we do in statics. But for a body to accelerate, it takes unbalanced forces to act upon it. Unbalanced forces cause what? Acceleration. And the net force from the unbalanced forces causes the acceleration that is produced. Causes what? Is very proportional to acceleration. So that's what it's saying, that F is very proportional to ma. Is that clear? So Newton's force is actually described as the where, for example, where the force acting on the body is 1 Newton, is 1 Newton. Force is measured in Newton. Force is measured in Newton, denoted by N. Is that clear? So 1 Newton, where 1 Newton of force is acting on a 1 kilogram mass, what will happen is that it will produce 1 kilogram acceleration. The acceleration produces 1 meter per second squared acceleration. So by the time we bring this in context of mass, F becomes kma, such that F is 1 equal to k times 1 times 1. So k therefore equals 1. So in that context, we are saying we define Newton's force as the force that produces the force that acts on a 1 kilogram mass. Newton's force is described as what? The force that acts on a 1 kilogram mass and produces acceleration of 1 meter per second squared. That's the way we generally define Newton's force. So generally we say that F is equal to what? ma. Now, but recall that I said it is unbalanced forces that cause acceleration, right? So keep that in mind, and let's look at what I want to treat here now. So what I am basically saying there is that if I have a mass, for example, I will soon start drawing what is called free bodies. If I have a mass and someone is pulling in this direction here, okay, and the person is exacting, so he's pulling in this direction and is exerting 50 Newton of force on it. And another strong guy here is pulling again. He's also pulling. This one is pulling with all his efforts and is exerting the same 50 Newtons of force. Now, will this body move? Now, this body will not move. Why? Because the forces that are acting on this body are balanced. Okay, but before we even deal with that, now let's say this body was not being pulled. If this body was on the ground, let's start with that. I'm sorry. This is where we're actually supposed to start from. If this body was on the ground, is there force acting on it? Yes. But then you ask me, why is this body not moving, master? Okay, yes, the body is not moving because the forces on the body are balanced. Now, they show me the forces that are acting upon it. Then I tell you that once a body is on the Earth's surface, that from the center of mass, this is called the center of mass, or COG, center of mass or center of gravity. That is where the highest mass, the weight of the body is felt, or where the body can be balanced by hand, where we can hang the body and balance, get it to balance. So that's the center of gravity. So where the highest mass is felt is where it acts as if the mass is concentrated. Okay? So this from the center of mass downward, the force acting upon this body is the weight of the body. And what constitutes weight? What constitutes weight is the mass of the body itself times the acceleration due to gravity of the earth. acceleration due to gravity of the earth, which is G. Is that clear? You should already know that. Now, but then you now tell me, Master, yes, that's the only force. Which other force do we have here? Now, if this was the only force here, naturally, this object should be going downwards. But why is this body on this surface? Why is it going downward? And you tell me it's because the surface is pushing it. Then you are correct, but you are not putting it in the right context. Because now if I told you that that was a force also, you might not believe. You might feel like, Master, the surface is rigid. So, I mean, something is blocking it. It's not like something is just blocking it. Now, what is happening is that there is a force between the surface of this body, at the base of this body and the top of this surface. In between that layer, there is a force that is acting directly upward along the same opposite path, and that force is called the normal reaction. R is called the normal reaction. But of course, this W is called the weight of the body. So the actual weight of the body is the force of gravity that is acting on the body. Is that clear? Let me repeat that. The weight of the body is the force of gravity, the magnitude of the force of gravity acting on that body. That's what we call weight of the body. Now let's go on. Like I said, the normal reaction is what balances it. So you can see they're in the same direction, they're in opposite direction, and they are acting opposite to each other. Remember, when we did forces, make sure you see my this thing on vectors. When you want to balance vectors, what do you do here in this case? In as much as they are collinear, so these are collinear vectors, what do? You basically take the arithmetic sum, right? Or difference. But it's actually sum, we call it. Do you know why? Because in this case, direction matters with vectors, right? So if I take R plus, if I want to add it with weight, I cannot just say plus W, because W here is in another direction, so that will be negative W. Now what happens is that it becomes 0. Okay, so that's why this body is not moving. I did mean that the weight of this body was greater than the normal reaction. For example, if this body was on the air surface, what will happen? The weight will be greater than normal reaction between air and the surface. So that body will keep going down. Is that clear? So for that reason, we know that the weight is the only one causing what? Causing acceleration. So weight is equal to ma. But A here, since it's falling freely under gravity, will be G. So we say mg. Is that clear? But in the context of this diagram I drew, this holds true, that is R minus W is equal to what? 0, which shows you that R equal to what? W, that is R balances the weight of the body. So just follow me, you're going to get it. So you can see already that even when there are no forces shown on the body has forces acting on it. So the diagram that shows the sum of all the forces acting on the body is called the free body of that diagram, of that body. Free body diagram. Now let's now go back to my analogy here. So if these two guys are pulling, this guy is guy A, this guy is guy A. Now let's call this guy Adeola, and let's call this guy, let's call him Williams. So if Adeola or Benga, no, Benga is strong, Benga is big. Let's call Williams. Okay, Williams. So Adeola and Williams are pulling this thing. If they exert the same force, what will happen to this body? This body will not move. Is that clear? Why will this body not move? Because the force in this direction, let's choose Adeola's direction as positive. If we choose Adeola's direction as positive, then FA plus that Williams force is acting in that direction, plus negative Williams force is going to be equal to what? 0. Why? Because 50 Newton plus minus that is minus 50, is going to be what? 0. So there will be 0 acceleration. However, now here, the acceleration is supposed to produce acceleration if they were unbalanced. But because they are balanced, 50 minus 50 is 0. So 0 no acceleration is produced. Is that clear? So however, if William had like 40 Newton, for example, was exerting 40 Newton. So what would happen in that case? What would happen? We would have that the force of Adeola plus minus the force of Williams will produce what? Acceleration on the body. Will lead to mass times acceleration on the body, right? So if that's the case, FA is equal to what? 50 plus minus 40. So that's minus 40 is equal to what? 10, which is equal to mass times acceleration. So what do we need to do to get the acceleration of the body is to know the mass, the value of the mass that they are pulling. Then the body will move by an acceleration caused by 10 Newton. Is that clear? So keep in mind, where did I get that F equal to ma from? From Newton's second law of motion that says that F is directly proportional to the acceleration that is produced. Or we simply say that it takes unbalanced forces to cause acceleration, and the sum of those unbalanced forces is directly proportional to the acceleration that is produced. Now let's now bring other mathematics into this equation. Other expressions rather. So since we know that F is directly proportional, F is now equal to ma, since we know this, then recall from kinematics that A is equal to change in velocity over time, right? So if that be the case, then we have F net, let's be putting net here so that you know it's net force, that's force causing acceleration, equal to mass times V minus U over T. Is this clear? This formula holds true. Let's call this one formula the first equation. Then this one will be the second equation. So if that is the case, then we can say that F net is equal to mv minus mu over t. Now, if you cross multiply this, that's such that we have F net times t is equal to mv minus mu. Now, mv, recall that mv is equal to the momentum of a body. Okay, the momentum of a body. So here, what you have here is a change in momentum. Now, what do you have here? F times s, F times t rather. So that is called the impulse. The impulse of the body. The impulse is the product of the force acting on the body times the time over which it acts. The time over which that force acts times the time. Product of force and time. So F times t here, you have here I equal to what? Ft. Keep in mind that this is not inertia, this is impulse. Now, then, what does that tell you? It means that the impulse of the body, the impulse on the body is equal to the change, because these are called the change in momentum, right? I said change in the momentum of the body. So it tells you that, this equation tells you that the change in momentum of the body, change in momentum of the body is exactly equal to the impulse that is felt by the body. So for example, you already know the formula for impulse to be force times time. And in an equation, in a question, you are not given force, you are not given time. Once you have your initial velocity and your final velocity, you know that the change in momentum gives you what? And you have the mass of the body. You can use it to calculate the impulse of the body. Okay, that is clear. So let's call this one equation 3. Now, before we, let's quickly consider the third equation. Then I'll tell you the third law rather, then we'll now go back to this second law, which we want to use to resolve equations depending on the shape, the type of this thing. No, we'll solve questions first. Let's solve questions before we and I'll show you how we use second law to resolve motion on inclined plane and the forces acting upon it, upon the body on an inclined plane. Now, keep in mind that we said that, okay, third law, let me go straight to the third law. Now, the third law is very simple. The third law simply says that to every action, there is an equal and opposite reaction. Okay, so someone even said that the Newton's laws of motion and especially the third one, first law, and Lenz's law are one of the most human laws in physics. Yes, what do they mean by most human laws? Have you discovered that when someone brings it hot for you, wants to fight you, you give the person hot, understand? Say, are you okay? Is it me? You say, I'm okay. Yeah. It's because to every action that you got from me, there is an equal measure of reaction from you towards him. That's why it is opposite. It is from him to you, and opposite is now you back to him. Do you understand now? So it is a human law. You understand? So, but of course, to teach you a basic lesson, you should not, your reactions should not be a product of people's action. It should be a product of God nature in you. You see, when people bring their actions, it is to provoke a reaction in you. So what you do is that you will blend God nature in your reactions, such that your reactions are not equal to an opposite to their actions. With that, it will create an acceleration in them because there will be unbalanced forces. Your own force will be greater because it is not equal to their reaction. It is now even greater than their action rather. So because of that, there will be an acceleration in them. And that acceleration is in that they will feel remorseful or feel like, what kind of person is this? All right, so that is the third law of motion. Now, let's solve some questions. Let me write some questions on the board and we solve. All right, now the first question says, a car of mass 1,200. So we have question 1, mass of the car is 1,200 kilograms, accelerated by a resultant force of that. So a resultant force or net force, okay? So the net force that caused acceleration is 3,000 Newton. For 0.5 seconds, calculate the gain in momentum. So it accelerates for how long? It accelerates for 0.5 seconds, okay? So a car of this accelerated by a resultant force, okay? So very simply, what we want to do is we want to calculate the impulse of the body. Calculate the gain in momentum. The gain in momentum is just, we want to calculate the, we have to know the initial momentum and the final momentum, that kind of thing, okay? So basically, you know that mass times acceleration is equal to force, right? And so we can also write it as force into mass into bracket v minus u over t is equal to the force. Is that clear? So this is the same expression. So this force is 3,000, mass is 1,200. So we'll put that here. V minus u over the time of impact is 0.5 seconds. Is it clear? So accelerated by resultant force of that, calculate the gain in momentum, okay? So is equal to the force, which is 3,000, okay? So basically, we'll cross multiply, we'll have, let's call this change in velocity, okay? Change in velocity. Change in velocity. The gain in momentum is going to be the change in this velocity times this guy, exactly. So that will be the gain in momentum. When we take the difference, is that clear? All right. So and I mean, of course, that you cross multiply here, and you will have that 1,200 times change in velocity is equal to half times this. That is 1,500. Okay. So pretty much this, the gain in momentum, that is how much momentum it's gained, right? It increased to. Okay, that will probably be, what's the change in velocity? The change in velocity is going to be 1,500 now divided by 1,200. Yeah. So this becomes 3F4 and 3F5. That becomes 1.25, so meters per second. So this is the change in velocity of the body. This is the change in velocity of the body. So you know that when a body moves, the mass, we're assuming that the mass is going to be kept constant. The mass, except something impacts on the body and then the mass breaks away in one way or the other. So if the mass does not break away, then the change in momentum of the body will be due to the change in velocity of the body, right? So the change in velocity of the body is this. Is that clear? But the gain in momentum, no, it gained this in momentum. It gained this velocity in momentum. Is that clear? All right. So, but of course, the change in momentum is 1,500, or the impulse is 1,500. All right. So, then number 2, a car of mass 1,800 kilograms moving at 20 meters per second, 20 meters per second, that's velocity equals 20 meters per second, is brought to rest. So this is u, because the final velocity is rest, that's 0. So over a distance of this, the distance s is 50 meters. Calculate the retarding force. Calculate the retarding force. So what we need to do is, knowing that v is 0, we know that v squared equal to u squared plus 2as. So in this case, v is 0, so 0 squared is equal to 20 squared plus 2 times acceleration times the 50 meters over which it moved. Then we'll have that this guy comes here, we have 20 squared, that's 400, is equal to 2 by 50, that's 100 a. But notice, as this guy is coming here to be negative, right? So since it becomes, now why does it become negative? It is to show you that the body is retarding, is coming to rest. So if the body were accelerating, A will be positive, but if A is negative, we've discussed that in kinematics. If A is negative, then it is retardation. So here, we divide both sides by 100, and A becomes minus 4 meters per second squared. But we are asked to calculate the retarding force. So, in which case we are saying that the force that acts upon it causes it to experience mass times negative acceleration. Make sense? So if that's the case, F becomes mass, which is 1,800 times 4, more like negative 4. So 4 times 18 is going to be 2 times 18, 36 times 2, 72. So F equal to negative 72 Newton. All right. So that is how to calculate the retarding force. This will be the retarding force. All right. The next one. A 6 kg object, the mass of the object is 6 kilograms, is to be given an upward acceleration of 0.2 meters per second square by a rope pulling straight upward. So if a rope pulls upward, so let's draw that in, let's put that in drawing. So the mass of this object is 6 kg. So it's to be pulled upward. It is to be caused to accelerate upward. It is to be caused to accelerate upward. So there is a force that is going to be acting in this direction upward, which is the tension. Now, whenever they talk about rope or string, inextensible string in this case, the force, there's always a force in that string or rope, and that force is tension force. Don't forget, the tension is the force in rope. Tension is the force in a string or a rope. Tension is the force in a string or a rope. All right. So if that's the case, what is the tension in that rope? Okay. So what we just need to do is draw the free body of this guy. Now what did I call free body? A free body diagram is a diagram that shows the sum of forces acting on a body. So the free body of this guy will look something like this. So just draw the body like this. Which force is acting upward? Tension. Which force is acting downward from center of gravity? That force is going to be what? The weight of the body. So they are collinear, the weight of the body. So now, which direction? So this is where you have to pay attention. Which direction is this body moving? The direction that this body is moving is upward. So all forces that are in direction of motion should be positive. All forces that are against direction of motion should be negative. I've showed you that before. When you in kinematics, if you throw an object upward, it accelerates upward with negative g. But if you throw an object down, it accelerates downward with what? Positive g. Why? Because downward is direction of acceleration due to gravity. But if you throw it upward, that is opposite direction, so that is negative g. So in this case also, any force that is in direction of motion, positive. Any force that is not in direction of motion, that is opposite direction of motion, not in direction of motion. Any force that is opposite direction of motion, negative. So now what's the direction of motion of this system? This system is to accelerate upward. So tension will be positive here. So we say T is positive plus, we want to add up all the forces. Now this weight, where is it acting? Weight always acts downward. We have said that, right? Weight always acts downward, straight downward. So if weight always acts straight downward, then this will be negative because downward is opposite the tension force. So this will now cause mass times acceleration on the body. So what we are doing is that we basically took the sum of all the forces, the sum of all forces. So and the sum of forces, what are the forces? Tension and weight. Is that clear? So we are basically saying that T minus W equal to MA. So what is, so T minus W is mg, right? Mg equal to MA. Is this clear? So we are asked to calculate the value of the tension. So let me bring this guy upward back, please. So this now becomes T equal to, this guy will come here, MA plus mg, or M into bracket A plus G. Is that clear now? So I'm very simply, we say that M is 6. So that is 6 into bracket A, which is 0.2, plus what is G? 10 meters per second square. Are we given? Yes, we are told to use 10 meters per second square. So if that's the case, then tension in the guy equals 6 times 10.2. This plus this is 10.2, so 6 times that, tension becomes 61.2 Newton, and that is the answer, 61.2 Newton. Now let's go to number 4 question. Now, 2 blocks of masses M1. What is the mass of M1? 300 grams. So let's convert that to kilogram. You basically divide it by 1000. That becomes 0.3 kg, right? 0.3 kg. You divide grams by 1000 to convert to kilogram. I hope you already know that. So an M2 is 500 grams or 0.5 kg. Okay? 2 blocks of masses M1 and M2 in contact with each other rest on a table. So both of them have initial velocities. Okay, they are in contact. So which means that they can accelerate together. So keep that in mind. Since they are in contact, they can accelerate together. So they have mutual velocity too. And the mutual velocity is what? 0. That is, they have the same velocity, which is 0. Now the coefficient of friction between each block and the table is 0.4. So now there is something called mu. I didn't talk about this. Mu is coefficient of friction. So mu is 0.4. Let me give you the formula for mu first. Now mu, on a table or on a rough surface, mu, there are two types of mu. We have coefficient of kinetic friction and coefficient of static friction. But either ways, if we're just giving coefficient of friction, we just use it like that. Because we have K, mu sub K and mu sub S. Mu sub K is when the body is moving, but it's still experiencing friction. Mu sub S is when the body is not moving due to friction. That's mu sub S. But here, we generally just say mu is 0.4 here. Now, what is the formula for mu? The mu is equal to the ratio of the frictional force to the normal reaction. The ratio of frictional force to normal reaction is what? Mu. That's basically it. Ratio of frictional force to normal reaction. So this is it. This is it here. Okay? Now, what must be the value of the force if the blocks are to have an acceleration of this? So what's the acceleration of the block? 200 centimeters per second squared. Okay, so we have to convert this to meter by dividing this by 100, right? So here becomes, divided by 100, that's 2 meters per second squared. Okay. Now, what must be the value of the force if the blocks are to accelerate with this? Now, it means that we have to do the sum of forces again, right? What are the forces acting on this body? The force, what will be the value of force? Okay, what must be the value of the force if the blocks are to have an acceleration of this? So it means that if the blocks must accelerate, I'm coming on. Let's draw it on the platform first. So this is our table. So there are two blocks, and they are in contact with each other. So block 1 has M1, block 2 has M2. Now, if they must accelerate, let's say the force is acting towards here. So what's the value of this F? Okay? But we know that friction is acting, right? Friction will act. What is friction? Friction is the force that opposes two bodies moving over each other. So simply put, friction is the force that opposes motion. So friction here is trying to oppose motion. Where is motion? We chose that direction. So friction will be acting in the opposite direction. Is that clear? But friction will be on both of them. So let's call the friction due to this one. Let's call it F1, FR1, and this one FR2. Opposite direction of motion. Is it clear now? So the sum of forces on this body now, on these our two blocks, is going to be the force that is in direction of motion, is our force that is trying to cause it to move, right? So plus minus frictional force due to block 1, minus frictional force due to 2. So when you add up all these forces, you give it the acceleration, the net force that produces the acceleration that is given there. Is it clear now? Add up all the forces should be equal to the net force which is there, which gives you an acceleration A. So by the time you have that F minus F sub R1 minus F sub R2 is equal to MA. Now, what is F sub R force? Recall that we said that frictional force, what will frictional force be here? F equal to, this times this, mu R. Is it clear? Now, what is R? Remember, when the body is on the horizontal surface, R is equal to what? The weight of the body. We did that in the beginning. So R will be equal to what? Mg. Is that clear? So that frictional force, therefore, will become what? Mu mg. Is it clear? So if that's the case, then frictional force is going to be F minus mu mg, mu 1 mg, minus mu m2g is equal to ma. All right. So let's start plugging our values. So what must be this force? Okay, keep in mind that this mass is going to be the sum of the two masses. So m1 plus m2. They're the ones that will accelerate together. Just keep in mind the two blocks are accelerating together. So this should be like m1 plus m2. times A. I hope you understand, it's still the same. The whole acceleration, since both of them will accelerate together, that's what is being assumed here. Okay? So in that case, we have this minus, what is mu? Mu is 0.4. Mu is 0.4 times, so we can keep this outside so that we use positive here. Like, let our equation become F minus, into brackets, mu m1g plus mu m2g equal to m1 plus m2 times A. Alright, so if this be the case, then F will be equal to F rather minus mu 0.4 times m1 0.3 times g, which is 10. We're taking g to be 10, okay? Plus, so let's use square bracket here. Then here 0.4 again times m2 is 0.5. Keep in mind I'm using 0.4 because it's the same for both coefficient of substitution, each block, you understand, between each block, both of them. So times 10, then close square bracket is equal to m1. m1 is 0.3 plus m2 0.5 times acceleration. What's the acceleration? 2 meters per second squared rather. Okay, so we can now solve our question now using calculator. Where's the calculator? So we'll now clean this place. So we are definitely saying that F will be equal to, all these guys will come here, or F minus, let's just say minus 0.4 times 0.3, more like this will be 3 times that, 1.2, minus 1.2 plus this 5 times this 2, that will be 2 is equal to 0.5 plus 0.8, 0.3, 0.8. 0.8 times 2, 1.6. So from here, this times this gives us 2.4. So F minus this plus this is 3.2. Okay? Is equal to 1.6. So F therefore must be equal to 1.6 plus 3.2. F is equal to 4.8 Newton, and that is the answer. Now let's go to a system of linked when masses are linked. Okay, linked masses. When the masses are linked, this one now is also linked, but it's joined. It's not just linked, it is jointed. Now what if the masses are linked with a rope? Now I want to determine the acceleration of the system. We are going to analyze about 5 of those components. We call them earthworks. So stay with me. Stay with me. Let me clean the board. All right. So now let's look at linked masses or linked acceleration. So we call the entire thing earthwood machines. Okay, it's earthwood machines that use this. It uses a pulley with an inextensible string. So the first assumption is that the string is what? Is inextensible. String is inextensible, because if it is extensible, string is inextensible. Because if the string be extensible, then these formulas I want to generate will not be useful, will not be the case. So the assumption is that string is inextensible, and in this first case, it is one string. So because it is the same string, tension will be same in the same string. Tension will be the same. So let's call this 1. 2, tension will be the same, will be equal in the same string. So that is, since it is if one string joins 2 things together, the tension in that one string will be the same. Is that clear? All right. So I guess that is it. So let's consider the simplest condition. The simplest condition is where we have an earth hood that looks like this. There is a pulley here and there's a rope that is like this. And the string now comes down here. Now let me show you something. If I call this M1 and I call this M2, let me ask you something. Looking at what you are seeing here, which of the masses is heavier? Is it M1 or M2? Looking at what I drew here, you see that it's as if this thing is already moving in this direction. So M2 is heavier. Is that clear? So M2 is heavier. Since M2 is heavier and they are linked by one inextensible string, then these equations I want to generate will work for them. So what will be the acceleration of this system? What is the acceleration of this system? That's the question. What is the acceleration of the system? Because we know that the entire system will accelerate together. So this is the fundamental question we want to answer all through in all the systems we will draw. Now for this one, it's very simple. What is the acceleration of this system? It's very simple. Now what you want to do is draw the free body for each of the body. Now it's not compulsory. It's not compulsory. You can easily show the forces. You can easily show the forces acting on each body. Let me show you how to do that. So basically on this body, what are the forces acting on it? From its COG, the force that will be acting down is weight, right? Which is equal to what? This mass 1 times acceleration due to gravity. Then there's going to be a force. Is there any force acting here or here? None is shown here, right? So we'll go to the next part, which is this top, which is the string that is attached. There is a force acting upward. And that force is tension. Then you ask me, how do you know that it's upward? It is because if I snap cut this thing, this rope will move upward a little bit. Will move upward to when it cuts, it will move upward a little bit to show you that something was pulling upward in the first place. Is that clear? So that is to show you, or if you have ever seen a rope cut little by little before, you see that it will be cutting and it will be cutting as if there is something pulling it on the opposite direction. So that's the tension. That's the tension. All right, so tension is upward in this direction. Now, how about in this case, for this guy, there's a weight 2. Weight 2 here is M2G. Is that clear? M2G, the weight of this body. Then there's the same force acting upward here, which is what? Still tension. Is it clear? All right. Now, then here goes our this thing. Now we can now analyze. So for body 1 now, for mass 1, what are the sum of forces acting on it? There is a force. Now we have to write it in direction of motion with respect to direction of motion. What's the direction of motion here? Clockwise, right? Because we said this one is greater than this one. The body will move, the system will move in direction of the higher mass. Is that clear? So since this body is moving in this direction, tension is upward, right? So tension is in direction of motion, but weight is opposite direction of motion. Weight is counterclockwise. Tension is upward, is in direction of motion. So tension is positive, then minus weight. Okay, so weight 1, we can call it weight 1, will lead to what? Acceleration of M1A. That's the net force. Is that clear? Will lead to the net force. So the tension therefore minus what is weight 1? That is M1G is equal to what? M1A. Let's write this equation in terms of T. Let's make T subject. Why? The reason is in your question, you will not be given the value of the tension. So if you are not given the value of the tension, then you just say T equal to what? M1A plus M1G. So it is M1 is common. So T equal to what? M1 plus M1 rather into bracket A plus G. This is the value of the tension here. Now, how about for mass? Let's bring it here. How about for M2? Now, for mass M2, what are the same forces acting? We still have the weight 2 and the tension. Now, direction is still downward like this, right? In this place, direction is downward. Here, direction is upward. Here, the direction is downward. Which force is up is in direction of motion? Is weight. So weight here, which is weight 2 or m2g, because weight is mass times acceleration due to gravity, mass times g, mass times gravity. So if that's the case, and it's positive here because it's in direction of motion, here this system is moving like this, so we'll call it positive, but tension is opposite here, so tension will be negative here. Is that clear? Keep in mind that it's not tension 1 and tension 2. I have said it that tension will be equal in the same string, so it's TT we are using because they are connected by the same string. So if this be the case, then this will lead to acceleration on 2, on mass 2. Is that clear? So in that case, we'll write it in terms of T, so that T equal to, T will go here, M2 will come here, and we'll have M2G, M2A will come here, minus M2A. If this be the case, then we are saying that T will be equal to M2 into bracket G minus A. All right. So what we'll now try to do is that since in equation 1, we found tension to be this, and equation 2, we found tension to be this. Since the tension is the same, then we equate 1 and 2. Equate 1 and 2. Equate 1 and 2. So what is 1? 1 is M1A plus G is equal to M2G minus A. I've released this video since. Okay, so it's very simple. Just focus with me. It's not hard, because some people, when we start deriving many equations, they always get bored. It's not hard. Just follow me. You will see that you can derive it by yourself. This is what I will do. In the next case, I might explain what to do. Now you will pause the video and first derive it yourself. And you now watch me derive it again. Is that clear? So now, here, we want to derive a term, an expression for acceleration. So since it's an expression for acceleration we need, we can write this as M1A. Let's open the bracket. M1A plus M1G is equal to M2G minus M2A. Now, why we open the bracket again is that I want to collect all the accelerations to one side. So we have the M1A plus M2A is equal to M2G minus M1G. This one comes here. Is that clear? So accelerations are now together. A into brackets M1 plus M2 is equal to M2G minus M1G. So if that be the case, then we are saying that acceleration will divide both sides by M1 plus M2. This takes care of this. M1 plus M2. So that we have acceleration, therefore, the acceleration of this system will be M2G minus M1G over M1 plus M2. So what was the use of this thing? The use of this PED, the use of this guy, this whole thing is to be able to find the acceleration of the system without the tension force given. So we can actually find it by just knowing the mass of the body. By just knowing the mass of the two bodies, we can find the acceleration of this system. Is that clear now? We can find the acceleration of this system by just knowing the masses, the value of the masses. If I plug this here, 10 is G is 10 constant, G is constant. Do you understand now? All right. Now, this is what you will do. Let me draw another simple system. Okay? I'll draw another simple system, and then you will try it. You pause the video and try it by yourself first. But I'll explain what you should do. So watch me first. Watch me. Look at this system here. So I put my pulley in this place. There is a mass M2 here. I just like to put M2 there. And I put a mass M1 here. Now looking at this body, there are two ways. In this one, we are assuming that the surface is frictionless. So let's first consider a frictionless surface. Frictionless surface. So if it's a frictionless surface, then frictional force will not matter here. But we also do a surface that is rough, a rough surface, frictionless surface. So if the surface is frictionless, and the assumption here too, listen, if M1 is greater than M2, where will the system move? Let me ask you first. If this one is greater than this, where will the system move? Will it move in this direction? No, it will not move at all. Exactly. So if they tell you that this body actually accelerated, check. The M2 is greater than M1. The one here is greater than this one. But once this body is greater than this system will not move. Is it clear? So if you are told to generate an expression for acceleration here, this is what you should do first. Now here, what are the forces acting on this body? There's just one force visible here. Actually, you know, the weight is acting downward, but there's also normal reaction counterbalancing it. So normal reaction upward and weight downward, they balance each other. So they don't add anything to the motion of the body. They don't add anything to the motion of the body. So because of that, we don't use them, both normal reaction and weight. So the only force that you can see here, since this surface is frictionless, no force is in this direction. So the only force you can see here is the force in this direction, which is the tension in the string. Is that clear? Tension in the string. So that's the force acting on this body. So it's only tension. So you can pause now and do it by yourself. All right. So let's go into it. I assume that you have done something when you have paused it. Now, so for this body one, the tension is acting in that direction, which is direction of motion, assuming that M2 is greater than M1 here. If the system even moves at all, M2 must be greater than M1. Is it clear? So what am I saying now is that now, let's now get the net force acting on this body. That if this system moved, then the force causing this guy to move is only the tension in that string. So the tension in that string is equal to the mass M1 times acceleration. Is it clear now? The weight has nothing to do. Why? Because weight is counterbalanced by normal reaction upward. Is it clear? Now let's go to the next case. Let's go to the next case. So this one is for M1 now. For M1. How about for M2? Now for M2, reverse is the case. Tension acts. Weight also does what? Acts. So if that's the case, the direction of motion is down in this side. So weight is positive. So M2G is weight, right? It's positive. Then tension is negative because it's opposite. It's opposite direction. So minus T is equal to the acceleration experienced, the net force that causes acceleration on mass 2. Okay? Okay? So keep in mind that the acceleration is the same because the systems are linked. Alright. So tension here therefore will be what? The same way we did it here. Tension. We did something like this here just now. See, we'll go here, this one will come here. So we have M2G minus M2A is equal to the tension. So tension is tension, so we equate them. So we equate equation 1 again, and we equate equation 1 and equation 2. So when we equate equation 1 equals equation 2. So M1A, that's equation 1, should be equal to M2G minus M2A. Let's bring the ones that have A together. So we have collecting like terms. We have M1A plus M2A is equal to M2G. Right? So if that be the case, then we are saying that acceleration into bracket M1 plus M2 is equal to M2G. So divide both sides by M1 plus M2 over M1 plus M2. So acceleration therefore becomes M2G over M1 plus M2. I want you to notice the consistency here. It looks like we're always just doing M1 plus M2 in the denominator. When we consider the third system now, we are going to know whether that is the case. Now the third system I want you to do, try this one for me now, is before we try it, I want to first draw it and show you something. Now this is on an incline now, on an inclined plane. So our pulley is still put here. Let's call this M2. Let's call this one M1. No. What if there was friction? What if the surface was rough? Before we do this, let's do the one where this surface is rough. I mentioned that I was going to do it. Now if the surface is rough, for surface with rough surface, for a rough surface now, friction will act on the rough surface, right? So if we have a rough surface, what will happen is that friction is going to be in this direction once the body begins to move. If this surface is rough, is that okay? So friction begins to act in that direction. And what's the value of friction? We said that mu is the ratio of friction to normal reaction. so that friction is equal to mu r, or friction equal to, since r equal for this body, r equal to mg, right? So mu mg, that's the value of friction. So now let's now analyze for M1. For M1, we know that friction is acting opposite direction of motion, since motion is in this direction. So friction will be negative, tension will be positive. So T minus, I'm not doing plus minus again, okay? So T minus friction, F sub R, will be equal to M1A for body 1. So what is friction? This is friction, yeah? So we have that T minus mu M1G. Is that okay? M1G equal to M1A because it's for body 1. That's why I needed to put the 1. So in this case, T therefore becomes M1A plus mu M1G. So this is equation 1. Exactly. So equation 2 still remains the same because we have not altered anything. So for body 2, for M2, we know that tension is still equal to M2G minus M2A. Is that clear? By the time we now equate 1 and 2, let's bring that here. I hope you're understanding it now. It's very simple. So by the time we bring this here, so we know that we now equate 1 and 2. Now let's equate 1 and 2. 1 is M1A plus mu M1G. So it should be equal to 2, which is M2G minus M2A. Is that clear? So if this be the case, we bring these guys together. M1A plus M2A is equal to M2G minus mu M1G. So if that's the case, then we have that A into bracket M1 plus M2 is equal to M2G minus mu M1G. Divide both sides by M1 plus M2 over M1 plus M2. This takes care of this. Then acceleration of the system becomes M2G minus mu M1G over M1 plus M2. So you see, you don't even need the frictional force. Just know the value of mu and you get your answer. So do you see how much? You see, it even looks like this equation somehow. We just subtracted this one and then we have that. Okay, so we are going now. Let's move to the next type where we have an incline. So make sure you concentrate on this one now. So this was the third case. So let's look at the fourth case. In the fourth case, we have an incline, okay, and a pulley that has a mass M2 dangling here and mass M1 resting here. Okay, now this body can move in two directions. Either move in this direction if M1 is greater, or move in this direction if M2 is greater. That one makes sense. But I like to choose this direction, okay? So I'm assuming again that M2 is greater than M1. So what you will do is that you can solve for when M1 is greater than M2, okay? And just screenshot your answer. Snap and send your answer to me on this WhatsApp number. So here's my WhatsApp number. And of course, you can reach out to me for any concept in physics that you want me to show you, or science generally, or chemistry, or maths. So like that. So I just like this direction, okay? I like it. So we're assuming that what M2 is greater than M1. We cannot just decipher here because the values are not given. I did 10 kg was given here, 5 kg was given. We know this system will move here. 10 kg given here, 3 kg given here, this system will move here. Exactly. So here we're assuming that M2 is greater than M1. But keep in mind that this is an incline. It's inclined at an angle let's say theta, let's just put theta there. Now if it's inclined at an angle theta, now the dynamics changes. So watch, this dynamics changes. You see, there is going to be, let's bring just this body now. Let's bring this body on this incline. Because this one is pretty much the same. It's pretty much the same. Now on this incline, there's going to be a force that will act straight downward relative to this body. What is that force? It's the weight. I've told you that before. So that will be M1G. It's going to act straight downward. But to know the value of the force that acts from this base, between this base, which we call the normal reaction, upward in this direction, which is R, we have to be able to, we have to resolve this weight. We have to resolve it here. Now, given this angle theta, now mathematically it has been found that here is also theta. Now let me just show you that. Let me just prove that to you. It's very simple. Now if here I have 90 degrees, if here I have 90 degrees, and this will be my triangle, kind of, this will be my triangle. If this is my triangle, I know that this place is theta. This place is 90 minus theta. If this is 90 minus theta, then this remaining place, since this place is 90, this entire place is 90, then this place must be 90 minus theta too. Is that clear? Let me explain that again. Okay. Now watch this. Oh. Another way to prove that, let's use numbers. If this 30 granite, let's use a sweet number, 30 degrees. I'm saying that this place will also be 30 degrees. Why? Because I know that if this entire thing here, look here, if this entire thing here is 90 degrees, then this place must be 60 degrees. If this place is 60 degrees, then this small angle here, if this is 60 degrees, look at this small triangle brought out here, this small triangle here, this place is under 90. If this is 90 degrees and this is 60, then this is what? 30. Is it clear now? So theta here is equal to theta here. So I hope I've proven that. So theta here. Now, so weight is acting downward. Now, so for us to know the value of R, we will resolve this guy down in this direction. How do we resolve it? By closing theta, right? So that will be W cos theta, or mg, in this case m1, so that will be m1g cos theta. So always remember, on an incline like this, the value of R, remember, is what? mg cos theta. Now, if this guy slides downward by a force, the force that causes it to slide downward, we can also get it by simply resolving. You know, these are vectors. You can easily just say this weight will resolve it to this direction by opening theta up, right? If we open theta up, it will become what? M, in this case, m1g sine theta, because you use theta sine to open an angle, right? Remember, when you open an angle, sine. When you close an angle, cos. Is it clear? So just remember this. So the force that causes the body to slide down the plane is m1g sine theta. The one that causes the body and the normal reaction of the body, m1g cos theta. So these are the forces that are acting on this body. Now, which force will be acting in this direction? Is the tension. Is it clear now? So we can now start for M1 now. For M1. Now, what will M1 look like? M1 will look like this. Will look something like this. What are the forces in direction of motion? Keep in mind that these two that I just analyzed here, they don't apply. They don't have any impact. Why? Why do they not have any impact? Right now, we are assuming a frictionless pulley. Frictionless plane also. Frictionless plane. Because if the plane has friction, we will bring in other factors. Is it clear? Now, I said that this is frictionless. So if it's frictionless, this mg cos theta does not have any impact yet. R does not have any impact. Weight right now does not have any impact. The only reason we needed the weight was to find the value of this guy. Why? Because this is the line of motion, right? So the force acting here is what? M1g sine theta. Is it clear? Good. So M1g sine theta is going to be acting downward. and this motion is going this direction. So tension will be in direction of motion. So tension is positive minus m1g sine theta. Is that clear? m1g sine theta. If that be the case, then don't worry, we'll solve question on this before we wrap it up. So this for m1 will be the one that led to acceleration on mass 1. Is that okay? Then if this be the case, tension therefore becomes m1a plus m1g sine theta. Okay? So let's call this equation 1. How about for m2? For m2, it is still the same. Tension reacts where? Upward. I don't need to be drawing free body for you. You already know how, right? Tension is upward, weight is downward. So weight is in direction of motion, so weight is positive. M2g is positive, tension is negative. So we have M2g minus tension is equal to the M2a on mass 2. So for that, this thing, we have that this one will come here, tension will go there. So M2g minus M2a is equal to tension, or tension equal to M2g minus M2a. So we can now equate equation 1, this is equation 2 now. So equate equation 1 and 2 now. Equate 1 and 2. Let me take other markers. So 1 is this, that M1a plus M1g sine theta is equal to M2g minus M2a. Okay? They will collect the guys that have acceleration together because that's what we want to determine. So M1a plus M2a is equal to M2g minus M1g sine theta. If this be the case, then A into bracket M1 plus M2 we are factorizing A out equal to this M2g minus M1g sine theta. Okay? So by the time we divide both sides, we have M1 plus M2, right? So over M1 plus M2. So that A therefore becomes, we can even factorize G out here, so that G into bracket M2 minus M1 sine theta into all over M1 plus M2. Notice again, we always have M1 plus M2 at the denominator. Is that clear? I mean, that seems to be the case. Okay, so that is that. Now let's go to, now what if there was friction on this surface? What if it's a rough plane? The plane is rough and we still want to move in that direction. The motion will be very hard. Okay? In fact, that mass that will cause motion will have to be very much greater than the other guy so that it can move when there is friction on that surface. So if there is friction, so when there is friction, such as occur on a rough surface, what will happen? Now listen. Here's what will happen. Here's what will happen. You see, these are our pulley. Let me redraw it. These are our M1. If the system is still moving in this direction, then here is F sub R that will be acting. But remember that the frictional force is going to be mu R from what we did, right? So mu R. Now what is R? R is, according to what we did here, R is mg cos theta. So FR will equal to mu mg cos theta. Is it clear now? So that will be the value of the friction here. Is that clear? That will be the value of the friction here. So in that case, therefore, we can say that for mass 1, the dynamics changes to tension is still in direction of motion, so positive minus frictional force equal to the motion on body A. So T minus mu m1g cos theta equal to m1a. So if this be the case, then tension becomes m1a plus mu m1g cos theta, equation 1. For our equation 2, for our M2, our equation remains the same. So for M2, because nothing has changed about M2, nothing has changed. So tension is still what? Tension is still M2G minus M2A. So if that be the case, when we equate 1 and 2, so if we equate 1 and 2 now, we have M1A plus mu M1G cos theta will be equal to M2G minus M1A. So let's collect these ones together. It becomes M1A plus M1A. Sorry, this is M2A, sorry. Plus M2A is equal to M2G is here, M2G minus mu M1G cos theta. Now you notice that it's just a slight difference in the equation when it is frictionless and when there is friction. So acceleration into bracket M1 plus M2 is equal to, G is common between M2 minus, you notice, M2 minus mu M1 now cos theta divided both sides by M1 plus M2 over M1 plus M2. This takes care of this, and A becomes G into bracket M2 minus mu M1 cos theta over M1 plus M2. So you can see that the difference in the equation is just this mu and cos theta. Is it clear now? So that's when there is friction on that surface. Okay, now, so it means that if you want to calculate acceleration for a system where there is friction, all you need is the mass of the object, the two masses that are connected, and the value of the acceleration due to gravity, the value of the coefficient of friction, and the angle of inclination of the plane. That's all. Now let's do one more system. Now, this system, you will try by yourself first. Try by yourself. It looks like this one, but it's very different. It's very different, or it's quite different. I'll just say it's quite different. Now, this one is where we have two inclinations, like this. Okay? Do you see this now? Let's make it a little bigger. So this artwood looks like this. And two masses are inclined like this. M1 here. M2 here. In this case also, I'm assuming that M2 should be greater than M1 because this system can move in any direction here. So if so this is also frictionless. You do friction for me and send it to me on WhatsApp to show me that you are getting it. So this one I don't need much. Now, these angles might be different and they might be the same. So in this case, I want to assume that they are different. Theta here alpha, here theta. So if this is the case, therefore, then for M1, let's try to draw the incline for M1. For M1, it looks like this. So this is M1. There is a force acting downward, which is what? M1G sine theta. This is the force that naturally wants to pull it down. Is that right? And there is a force in this direction, which is what? Tension. So those are two forces that are of consequence here. So now, if this motion is in this direction, clockwise again, then tension is positive, right? Because tension is in the direction of motion. T minus M1G sine theta will be equal to M1 A. So that T equal to M1A plus M1G sine theta. It looks like the first one we did, like this one. But so this is for M1. For M1. Now, but for M2, let's see what changes. M2 is now like this. There's a mass M2. Now there's a force trying to pull it down here. That force, just like here, is going to be M2G sine, but this time alpha, not theta, sine alpha. Sine alpha. So that if that be the case, then we'll be acting upward on that rope. Tension again. Tension is opposite direction here. This one is in direction of motion here. So we have M1, inclination is alpha, inclination is theta. So here, M2G sine alpha is in direction of motion minus tension is equal to M2A. So if this be the case, then tension therefore becomes M2G sine alpha minus M2A by the time they interchange position. So this equation 2 is equation 1. By the time you equate 1 and 2, what will happen? M1A plus M1G sine theta is equal to M2G sine alpha minus M1A. Is this clear now? So if that's the case, collect M1, MAs together. Sorry, use M2A. Just make sure you are not making any mistake. M1A plus M2A is equal to M2G sine alpha is what we met there minus M1G sine theta. Is that clear? Let me take water. So A into bracket M1 plus M2 will be equal to this. So by the time you divide both sides by M1 plus M2, we divide this side by M1 plus M2. So that A becomes M2G sine alpha minus M1G sine theta over M1 plus M2. Now, because of time, I want you to go home and by yourself. What if it's an equilateral, an isosceles triangle where these two angles are the same? If the two angles are the same, tell me what will happen here. The dynamics that will change here. You'll notice that there is something that can already happen here. You understand? So try by yourself and show me what the case will be. And also post that in the comment section. Try one where we still have our incline, our masses M2 here, M1 here, and here is theta, here is theta. So try it. Try this one. Alright, so that will be it. Now before we solve a question, okay, let me solve one question, and I will now take it to bodies inside an elevator or a lift. Let's see that too. I'm sorry, I'll have to just quickly wrap it up because my phone is critically low. My phone power is critically low. So let's quickly just take motion, weight of body in lift. Weight of body in a lift or elevator, right? Now, this is it. First, know the following, that any force that is not in direction of motion, positive, no, negative. Any force in direction of motion, positive. I reiterate, any force that is not in direction of motion, negative. Any force that is in direction of motion, positive. So now, what is the weight of a body on the lift? How does it change? It changes with respect to the position of the lift, the dynamics of the lift. So what the spring balance, if you put a spring balance under a person in a lift, what the spring balance will record is the apparent weight of the body, which is the R. R is the apparent weight or normal reaction between the sole of the feet of the person and the surface of the spring balance. That's the normal reaction. Is it clear? So now, in various scenarios, this will change. This value will change with respect to the weight of the body. Is that okay? The weight of the body is the actual weight of the body. The apparent weight is the normal reaction which the guy records, the spring balance records with respect to the dynamics of the elevator. When the elevator, for example, when the elevator is stationary, or lift stationary, I'll be telling you the consequences of all of this. When the elevator is stationary, for example, what will happen? The R, now, if the lift is stationary, the lift is not moving, the weight of the object will be exactly equal to the normal reaction. So what will be recorded, R, will be equal to the weight, which is mg of the body. So the actual weight of the body is recorded when the lift is not moving. So that's case 1. In case 2, the elevator is moving upwards. Now, in this case 2, when the elevator is moving upward, now, upward is the direction of motion. Remember, so this is the body, for example, upward is the direction of motion. Now, for this body, the free bodies include the weight and the normal reaction. So, the normal reaction is going to act on this, on the same line, okay? Normal reaction is upward. So, which of these is in direction of motion? Which of these? Normal reaction is in direction of motion, so it will be positive, R. Then weight is not in direction of motion, weight is down. Lift is going upward. Normal reaction acts upward too, right? So R will be positive, weight will be negative, so minus W will be equal to the acceleration experienced by the body. Is that okay now? So if that be the case, what will be the R that will be recorded? The normal reaction is what is recorded, equal to the weight plus the MA, or MA plus weight, which is mg. So R equal to MA plus mg. This is why when the weight is going upward, the body feels heavier. The body feels heavier. Okay? The body feels heavier. So R equal to M into bracket A plus G, either way. Now, how about case 3? Case 3. Case 3 is where the elevator is moving downwards. Moving downwards at less than G. If the elevator is just moving downwards a little bit, now let's take again. If it's moving downward, now direction is down. Which force is in direction of motion? Weight. So that will be positive. So W will be positive. Then the normal reaction is going to be negative. Minus R is equal to the acceleration that will be experienced by the body. Because the acceleration will be slow, right? So if that be the case, let this guy go here, let this guy come here. So weight is mg minus ma equal to R. So the R that will be recorded by the spring balance will be equal to m into bracket g minus a. So that is the other formula. Then the fourth case. So what will happen here? The body, you in the elevator, you feel lighter. Okay, you feel lighter. You feel lighter. Now, let's now take the last scenario where the elevator, maybe the cable has broken. So the guy is just free falling. You understand? The cable is free falling. The elevator is free falling. Elevator free falling. So it will just be like when the body is free falling, right? So if the body is free falling, weight is in direction of motion, right? The normal reaction is not in direction of motion, but to be equal to the acceleration of the body. NA here equal to MA, but A here is going to be the value of the acceleration due to gravity, because everybody is free falling inside the elevator. So A will be G. Therefore, W minus R will be equal to what? Mg. Is that clear? So if that be the case, R goes there, then W minus mg is equal to R, so that R equal to mg minus mg. So R equal to 0. So for that reason, the body feels weightless. The body feels what? Feels weightlessness. That is, it has 0 weight. So 0 weight to be recorded by the spring balance. Alright, so now let me solve one question on the former one and one question on this, and we'll wrap up the video. Okay, so these two questions are the only questions we'll solve, and they are simple. Okay, so look at this one. This one will simply drill this for us and say we should determine the acceleration of the system. Very simply, using the free body diagrams that we just learned, we say that for M1, let's call this one M1. First, where is this body accelerating? Down like this, right? Because this guy is greater than this guy. So if the body is accelerating in this direction, then we know that for M1, tension is positive because it's in direction of motion, but weight of this body, m1g sine theta, m1g sine theta is negative, right? So minus m1g sine theta is equal to m1a. This is where I quickly analyze it. Then t equal to m1a plus m1g sine theta. I'm redoing it because I can't remember the formula we generated. So that's why you must know how to generate it yourself. Then for body 2, for mass 2, for M2, we know that T is negative, right? So M2G is positive because M2G is downward, minus T equal to M1A, equal to the acceleration. So this guy goes there, then we have T equal to M2G minus M1A. By the time we equate them, we equate this guy and this guy. We have M1A plus M1G sine theta is equal to M2G minus M1A. By the time you collect like terms, we have, M2G minus, M2A, acceleration on body 2. Acceleration on body 2, please. M1A plus M2A is equal to M2G minus M1G sine theta. If that be the case, A into bracket M1 plus M2 is equal to M2G minus M1G sine theta. Divide both sides by. Then you are asking yourself, now do I have to do this all the time? See, by the time you master it, you see how fast I am, you even be faster. Is that clear? So A therefore becomes M2. What is our M2? 15. Let's first write the equation. M2G minus M1G sine theta. You see, I'm so sure I didn't make a mistake. Is that clear? All right. So M2 is 15. M1 is 10. That's all. That's all you need. And theta is 30. 30 granotes. And usually they give you a very sweet angle for this kind of questions. So we have A therefore becomes M2, that's 15 times 10 minus M1, 10 times 10 sine 30 granote over M1 plus M2, 15 plus 10. So here A therefore becomes 150 minus sine 30, half of 20, 10. Half of 100, sorry. Half of 150 over this plus this, 25. So A becomes, I hope you are getting me. Half of 10 is 5 times 10, 50. We have this minus this is 100 over 25. Here 1, here 4. So A acceleration becomes 4 meters per second squared. Is it clear? Then for the second, the second question. For the second question, should we to accommodate this place? It says that a man of mass, the mass is 60 kg. The weight of the man, the mass of the man is 60 kg. Stands in a lift. Find the force exerted on the man by the floor. So the floor is exerting force on what is that? Normal reaction. So R will be equal to, when the lift is number 1, moving upward with A. So acceleration is, you are looking for this, acceleration is upward 1.5 meters per second squared. So you just say Just go and use when the body is moving upward. This is the formula. Okay, for you to remember, just remember that it's heavier when you feel heavier when you are moving upward. So that will be plus. Okay, but minus when you are moving downward. Exactly. But be sure remember that it's mg minus me in this case. So R will be therefore equal to m into bracket A, which is 1.5 plus G, which is 10. What is our mass? 60. So R equal to 60 into bracket this plus this, 11.5. So 60 times 11.5. That is 690. So the answer here is 690 Newton. Then the second question says, when the body is moving downward with that acceleration, very simple. R equals to m into bracket G minus A, because that is downward. The body will feel lighter. So R will equal to m, which is 60, into bracket 10 minus 1.5. So you see that what you get is actually going to be less than the actual weight of the body. So here, what we got is greater than the weight of the body. So 1.5 minus that's 8.5. So 60 times 8.5, 510. 510 Newton. So, and this proves that we are correct because you feel lighter when you are coming down. So that shows you that, and your normal weight, since this body is 60, then your normal weight should be 600. So 510 is less. Is that clear? So with this we come to the end of the video. Do well to subscribe to the channel and make sure that if you need questions on this, I have numerous questions on this. Just connect me on that WhatsApp number and I'm going to send the questions to you. God bless you as you subscribe and share the video with your friend, please. It took so long to shoot this video. God bless you.